In this video, I'll talk about a different method to measure turns ratio when the neutral of a Y is not accessible. In other words, the neutral is not brought out and it's not grounded, so you can't access it, so you can't measure phase to neutral voltage. In a previous, there's another video that I made which kind of it's a different method basically. This is another well-known method which is documented in IEEE, for instance. So a lot of material here is from kind of IEEE. So we want to measure, for instance, so if I call this, phase A. So if you think about a transformer in general, in this case, I'm just thinking core form. So we have three phases. So here's a three-leg core for simplicity, but there are other technologies like four-leg core, five-leg core, shell form, and so on and so forth. So this is kind of the core. Then you have the windings. So you would have low voltage, for instance. Then on top of it, you will have high voltage. So they're concentric. So you have core, then low voltage is wound over it, then high voltage. So you would have the same thing on the other leg here. And those coils basically, they have turns, to get the proper voltage. So I'm just kind of showing the overbuild. So these are HV and LV coils which have turns basically. Obviously you might have tertiary, you might have a regulation winding and all kinds, but for simplicity, now because if I call this phase A, phase B is in the middle, and phase C is kind of the other leg. So because when you energize the high voltage, for instance, flux will be induced in each core leg, and that flux will kind of link or try to link the other winding to induce voltage in it. So now the way we kind of represent that to show like, okay, phase A, which high voltage, which low voltage, schematically, the way you would show that, for instance, this is what I'm showing phase A. So I'm going to highlight phase A here. Then I'm going to find in the Y side the phasor that's parallel. So you take because it's parallel, so those are kind of in phase because they're wound around the same core leg, and they will see kind of the same flux will kind of link them. So then, B phase, so I'm showing B phase here. So then I'm going to find the parallel, which is this one. So those are wound, so they're parallel, that means they're wound around the same core leg. So then find another. So then phase C, so if I highlight phase C here, then I'm going to find the one that's parallel to it on the low voltage. So they're kind of color coded. Each parallel pair means they are wound around the same core leg. So now, if I want to apply the turns ratio, because you see this neutral in the Y here, because think about from the tank, I only have H1 bushing. If you're looking from the top, H2, and the windings are inside, then I have X1, X2, then X3. So when I measure the turns ratio, I can connect H1 to H2, for instance, then I can measure. So this would be the source, but also I would measure the voltage between. So that would be, for instance, the voltage measured on the high side, which is basically what was applied minus some voltage drop. Or actually it would be then what was applied basically. Then I'm going to measure the voltage on the other winding. I call it V2. But the problem is you have a delta. So when, in other videos I kind of talked about this. When you have a delta, the line voltage is equal to the phase voltage. But when you have a Y, the line voltage equal square root 3 times phase voltage. So there's a factor of root 3. But to measure the phase voltage, because when you do voltage ratio is equal to the voltage in HV, which is, in this case, it's phase because it's a delta, divided by V, LV, phase. That way I don't have to worry about the factor of, root 3. But since my Y, I can't access the neutral, so this is the neutral, because it's not brought out. So I can only measure line to line. That means there will be a root 3 in a factor. So one way you can measure the voltage ratio or turns ratio is by this method. So I already talked about one method. So this is kind of the second method. So what you do, for instance, I want to measure the voltage for phase A, and I kind of like IEEE and other documents, uppercase A, lowercase a, just to kind of make a difference between uppercase A is a high voltage, lowercase a. I guess I could have called it AH, the other one AL or something. To make it simple, uppercase A, lowercase a means phase A, basically. So then what I do, I kind of connect a voltmeter across, because this is phase A between H1 and H3. Then I connect a source between H1 and H3, which is phase A. Then because I have phase A here, so I can short from H2 to H3. So by shorting it, basically as if it doesn't exist, so the flux in this phase C here will be eliminated because it's shorted. So then if I look at phase C, which is here, it's basically, there will be no flux, as if it's shorted basically, because it's the same, no flux will be kind of. So what I do, I create like a virtual neutral basically. It's like a virtual neutral, because no flux will be induced because I shorted phase C on the high side. So phase C on the low side will also be as if it was shorted. So no flux will be induced. Now I can measure from X1 to X3, but keep in mind this phase is kind of shorted. So it's as if I'm measuring from X1 to this neutral point. So it's basically, I'm measuring phase to neutral basically. So by shorting this phase here, I created like a virtual neutral. Then I don't have to worry about phase to neutral, line to line, or converting back to line to neutral. So this is for phase A. I can do the same thing to measure phase B. So if I want phase B, because if you look, phase B is here, phase B is here, but the problem is I need to get rid of this here. That means I have to short phase A. So by shorting it on the delta side, so no flux will be created because it's shorted basically. Because think about it, if this is the core leg, you have the high voltage winding, then you have, sorry, I'm going to extend this here, then you have the low voltage winding, because I shorted I shorted this phase, for instance, that means no flux. Flux will be 0. That means this here acts like it's shorted basically. That's what I'm doing. Now phase A is shorted basically. So then I'm measuring from x2 to x1, but as if x1 is basically, because x1 is just connected to the neutral. So it's as if I'm measuring from here, from x1 to here basically. So that's what I'm doing. Then I can do the same thing for phase C. So I want to measure phase C. Phase C is here, then phase C is here. So these two are parallel, but the problem is I need, for instance, I'm going to measure from x3 to x2, so I have to short this here. So that's why it's shorted. That way the flux will be eliminated. So then I can measure from x3 to x2, but really I'm not measuring line to line. I'm measuring from x3 to the neutral basically, because the B phase here, you know, it's like it's not in the circuit because it's short. That phase is shorted, so flux will not be induced. So this is another method to kind of measure the turns ratio when you cannot access where this neutral basically of the Y. So the neutral is, sometimes people say it's floating, which means it's inside. So it can't be accessed. So you have no access to it. In other words, you cannot connect the voltmeter to it. So this is another method you can measure the turns ratio. Thank you.